The signal generator, driving a vibration generator, and if we change the frequency, you'll see we'll start to pick out this quite distinct vibration here, going like that. We're getting maximum vibration here, maximum vibration here. If I put maximum amplitude here, zero amplitude here, zero amplitude here. That's the most comfortable place for that standing wave to be in this length of string. Really what you've got is the wave starting here, going back on itself, meeting itself in the middle, and you've got constructive and destructive interference because of the wave actually catching up with itself by being reflected. So that happens with strings. This is why guitar strings and any stringed instrument resonates at a particular frequency, because the length suits one particular frequency. So you've really got two full wavelengths across the length of the string, the way I've got it set up at the moment. Now, so at that point there, we're getting maximum, you won't see it very well from it, well, I don't know, maybe you can see it. So we've got half a wavelength there, half a wavelength there, and half a wavelength there. So we've got 1.5 wavelengths going around it. If we increase the frequency, you need the right number of half wavelengths to fit into this circle. So instead of the string being stretched out, we've got it set up in a circle now. So for an electron to go round that circle, it needs to fit into the right number of wavelengths. Otherwise there's energy lost. This was the problem that classical mechanics had with electrons orbiting, in that classical mechanics said that if an electron is a charged particle, is accelerating towards a positive proton, then there's going to be energy lost because it's accelerating, therefore there's a force, there's work done, and so it wouldn't be able to do that. Because the electron actually behaves as a wave, it's got wave properties as well as particle properties, then it sets up this standing wave, this resonance around the electron's orbit. But the thing is that the electron can only orbit at particular circumferences, because it's got to fit in with a certain number of wavelengths that the electron has at those particular energy levels. So got saying that, okay, you've got these orbits and around a positive nucleus, but the only allowed orbits are those that have an angular momentum, and the angular momentum is the mass times omega. So, sorry, MVR is the angular momentum, which you can get because angular momentum is mr squared is the moment of inertia of a particle times the angular velocity, which is v over r. So 1r cancels there. So MVR, the angular momentum of the particle, Bohr postulated, was just a particular number times Planck's constant. And it was a sort of one of the sort of big leaps of faith in physics, where he said, right, well, this is just an idea that I've got, guys. You know, stick with me on this one. I think this will work out. And after a couple of years, they were able to get the experimental evidence that did show that angular momentum was quantized. That's Planck's constant. That's the 6.6 times 10 to the power minus 34 joule seconds. That's just any integer where the integer depends on the energy level that you're dealing with, and 2 pi is just a constant in the equation. So Niels Bohr sort of came up with this almost out of thin air. He just had a hunch based on the atomic spectra. And also these series, the line series, which we'll come back to, the Balmer series and Paschen series, these are all to do with the different energy jumps within a hydrogen atom. They're always dealing with a hydrogen atom because it's the simplest atom. So a lot of this early work was just on a single proton with a single electron, but it seemed to fit from there. So that's the quantization of angular momentum. What we're then going to do is take that on, once you've done the electrical phenomenon unit, is to actually build up the equations which give you those line spectra. But that needs a bit more to do with the electrical forces involved, first of all. Going beyond that, Stas had on his model of the atom these electron clouds, where he's saying, well, there's a cloud of electrons here in this sort of area, but we can't exactly say where. But there's a good probability of getting electrons here. There's not such a good probability of getting electrons here. This probabilistic model of the nucleus is much more in line with quantum physics and also Schrodinger's equations, which build up a sort of probabilistic way of working out where the electrons are, and just said, instead of saying, right, there is an electron here, because as soon as you try and look for that electron, you change the conditions at which the thing that you're trying to measure, which is the whole business of Schrodinger's cat that we talked about just briefly last time. Okay, so that's what you need to know. It's, I would say, fairly unsatisfactory in that you're being given just this glimpse of this is wave-particle duality, and that's the bit that you need to know of. It doesn't go a lot further into explaining why it is. What you could do is you could probably spend half an hour with Scholar or any other website, and you get a much better introduction to it, a much better flavor to what the actual wave this means. But in terms of what you need to know for advanced higher, that's about as far as we need to go, just that the angular momentum is quantized. That's how it's quantized.